Morning, everybody. My name is Richard Percival. I smile in a very fetching way. It's one of my advantages. I'm very friendly. That means you may ask questions at any time, and there is no such thing as a stupid question. So, I work with some colleagues from Europe. I'm the American end of Microenergy Experts Group. We have a guy in Germany and a guy in France and a guy in the UK. In the recent past, I was Director of Strategic Accounts at Infinite Power Solutions, a company you never heard of, which has now disappeared. But it went out in a truly spectacular fashion, and we'll go into that. And prior to that, I was a consultant for Solidcore, who've just changed their name under here. They're called Bright Something. It's a great name, and I've already forgotten it. But they're a partner, and they have a stand. Look for Bright Something, and they make batteries, thin batteries. And a long time ago, I spent 10 years as Director of Applications at National Semiconductor Europe. And below there, if you interact with Richard Percival on LinkedIn, I am happy to accept anybody who knows me. In other words, you now know me, or you will by the end of this session, for better or worse. Okay, obviously you're participating in DevCon. I have been blown away by the quality of this work, this presentation, and particularly the keynote address. And it's kind of interesting because I wrote this paper for some earlier roaming DevCon sessions that took place in places like Mexico. And I needed to grasp something that would bring this together. And I came very close to your keynote address. I didn't get the connected automobiles, because that's really aggressive. But such a vision, such a powerful thought. I mean, it is an absolute catalyst for really successful collaboration. So I'm just blown away. So this is a quick reminder from our sponsors what Renesas does, and I think you know that already. So what you came here to learn about is ultra-low power solutions for wearable tech and the Internet of Things, Internet of Everything. You want to know how will systems look and function when there's no conventional power source. Is this going to affect the way my organization interacts with the market? And are there parts that I can see working now? And there's a couple of those links again, and we'll go back to them a little later. So we're going to first of all say that the smartphone and the cloud changed the game, and that's the one which I got there before the keynote did. And then we'll describe a typical low-power sensor. We'll go into energy harvesting, a complete grounding on energy harvesting, the things that we who were in the energy harvesting or started in the energy harvesting business 7, 8, up to 10 years ago, what we've learned. Then we'll have a working beacon example. That's the reason I've got you participating by turning on your phones. And then we'll summarize, and I'll take any questions that are left over that you didn't come up with during the presentation. So we're seeing all kinds of numbers. That was key, stated in several of the presentations as well as in the keynote. Number of connected devices per head of global population. And this is the scary bit, because we're talking about people who currently are on $2 a day. And yet they are the global population. We're 7.6 devices per person, including the people who are currently unbanked, unconnected. So it looks as if they're going to be connected. And funnily enough, that's exactly what is now possible. So just as Africa has taken the mobile phone on and suddenly got money transfers occurring across the phone network with no banking network and no phone network, just solar-powered cell repeater towers, you suddenly realize that the new technologies are actually changing the way the globe can grow fast. And it's a privilege to be part of that revolution. I hope you're as excited about it as I am. So, as a result of this connectivity and a lot of work by a lot of people over the last couple of decades, the network is now always on. The main processor is in the cloud, and there'll be an app for that if we know who wants which data and will pay for it. It has to be monetizable, it has to be valid. So then we ask the question, how little data can be enough? Because of course data costs money to generate, and it costs money to transmit and to store. The storage we can forget about. The cloud, to all intents and purposes, is almost free. But we do have to monetize, and we have to be conscious of where the costs are coming from. And then, of course, the ultimate $64,000 question, how to power the sensors and the data transmission and the storage. But a solution exists if you can formulate a query and the data can be accessed. So, according to Markets and Markets report from last year now, IoT should be growing to ridiculous numbers. The main thing is a compound annual growth rate of almost 30%. So if this is a great place to be, because basically the rising tide will float all boats. And so this is one way of looking at it. In fact, this presentation comes from one of the previous presentations yesterday. The low power wide area network. They were particularly looking at LoRa standard. LoRa standard is maybe 50% of the expected market. But you can see how you can add these numbers up and you're rapidly arriving at these strange number of billions. You know, 7 billion people times 7 devices is 49 billion opportunities for there to be a device that needs to be connected. And this is best estimates. And in the middle, you can see the sort of pretty pictures of the kind of places where devices are being installed. So where's the market from my point of view, or from the energy harvesting point of view? It's obviously at the edge. So we start with body area computing, which is the stuff which is on people who don't wish to be plugged into the wall. And in that area, the big growth areas are health monitoring and predictive analysis. This is a huge opportunity. I mean, you think about being able to pre-diagnose diabetes from the way people walk. So all you need to do is to give them a pair of shoes, which is self-powered, and which connect to a wall wart, and it says, Mr. Smith got up this morning, he put his slippers on, he walked to the bathroom, and he's not walking quite right. We extract the intelligence from that, and the doctor now knows that he's not as well today as he was yesterday. So you have the ability to, with people, just the same way as you can watch a machine having a bearing that goes noisy, which is another application. I believe the next speaker in this room will be talking about industrial uses. There are so many places where the health and monitoring and predictive analysis for people and machines and objects, will all benefit from the same ideas. Shopping, loyalty, coupon, and secure payment systems. We all know that Apple finally landed on with Apple Pay, and that unleashed the NFC world. But the whole of the world was waiting for NFC. You may not have noticed, but the people who had put money into it were waiting for it. And it hung fire for 10 years. And then Apple says, we'll do a payment system. And suddenly the floodgates open. And the key thing is this sector is exploding because of the smartphone is a portal. Then we have more traditional, what used to be the major market, which is plant, pipeline, infrastructure monitoring, automation and control. Characterized by low data rates, dangerous and hostile environments, and key thing, a high cost of downtime and the high cost of access. Sending someone out in a desert to fix something that has gone wrong is massively expensive. What you should be doing is predictive analysis. You should be aware of a failure that's going to happen so that you can run a tour that runs up and down and does the things which, basically the squeaky wheels will be getting the oil. And predictive maintenance therefore replaces routine maintenance. The wireless standards have to offer complete security to gain traction. I'm pleased to see that we've had presentations here already in which that is now becoming demystified. The partnerships that Renesas have got in this area are impressive and important. And then finally, energy security and comfort in the built environment. And you've seen the growth in either occupancy centers and California Title 24, but also the retail sales of Nest, and the fact that Nest has become a property that might be bought by somebody because it's such a good thing to be in home automation. The key reason for this is, as was proven by Enocean in Germany, which came out of Siemens some 14 or 15 years ago, you can build a building now with 50% saving on the capital expenditure if you don't put wire in it, if you do it wireless. And as soon as you put the controls in place, you can assure a 40% energy savings. The idea that that is not already standard practice it boggles the mind. The conservatism of people is hard to beat, but the truth is the installation people don't really have an incentive to do it because they don't get rewarded for how good the building is 50 years from now. And we haven't got a link which says, if I build this building better, I will be rewarded for being green 50 years from now, but I will get rewarded if I get the contract by putting in some cheap stuff. And so we have this trap, and good luck to all the people doing LEED and green building and all the initiatives that try to get people to be conscious of the value of saving energy and saving capital expenditure in the built environment. So what joins these things together? Now, certainly, it's the wireless services available through the smartphone. So going around in the circle, and what's going to be the trendy device is always very hard to predict. I rather like the ring on the right. Does this thing work? Yeah, that's a key to it's a device with a near field communications, an RFID device essentially, which means as you bring your hand close to an object, the object will recognize you, and then you do whatever it is that you want to do there, and it's only going to do it for you because you're authorized and pre-coded. And as we learned in the security, that ring, the content of the code can be checked. Which factory made that ring? Has that ring been reported stolen? Where was it made? When was it made? Is this guy still a valid user? Has he paid his fees? Or an entire security check. But the user doesn't even think about it. He just simply goes up and does what he wants to do. And that, of course, is the place where this kind of automation is so powerful. Then we've got the Apple Watch, of which more later. Here's a shoe that generates power for basically seeing whether you're moving, how you're moving, where you are, the rest of it. Just an insert that goes into a shoe. Pill machines that tell you whether you've taken your pills or report to the doctor that you've taken too many. Things for refrigerators that say that you've run out of eggs. Smart door locks, thermostats, and even that dog. We shall see if what comes of that. It hasn't quite taken off. So you notice the thing about all those things is that they tend to be away from the mains, away from the power. So where can you get energy from? Well, it's many and various, and it keeps on getting better, because now that we're thinking about it, thinking about sustainability and thinking about how we can do it, then we start finding energy all over the place. So by looking at, obviously the winner so far is solar, because we all get it. Thank you, Mr. Einstein, who got a Nobel Prize for the photoelectric effect. Interesting, the distance of the time between him just predicting that a photon making electricity or releasing an electron was important to getting his Nobel Prize was, I think, 14 years, which goes to show nothing's changed. The really good discoveries take a very long time to become understood. Now, where do these things go? Well, it matches precisely with the markets that we've already described. The RF comes in various flavors, and we'll talk about them. The thermal, the magnetic, and magnetic comes in, again, flavors, and I'll show you some examples of these. So let's look now at a typical low-power sensor product. The assumption is that we've got some form of ambient energy and a transducer that's built into the device, which will respond to whatever energy is available, and it's very variable, and it'll try to do a job. The key thing it's got to do is to power radio, and therefore the first thing you should spot is that you can't use an energy transducer which is not producing enough energy to power a radio unless you store it up, build it up, have it nicely packaged, and then go. You've got to go with your energy and make a short pulsive radio, and now you've used up all the energy that you've stored, but you just did the job. So energy storage is sitting right here. Then, of course, the rest of it is the Renesas stuff, and the semiconductor stuff is on the board as well. Then the options occur in wireless frequencies, protocols, energy sources, actuators, displays, keys. Plenty of room for imagination here, but the basic architecture is pretty well always like this. So energy harvesting is collecting energy to power a mobile or remote load. Energy can be collected from ambient or radiated light. So you can either have the light or you can deliberately shine a light. Heat, movement and vibration, or it can be picked up from an invisible electromagnetic wave. You can deliberately transmit energy, and we'll talk more of that. Harvesting refers generally to small collection fluxes measured in microwatts to milliwatts. Low power design techniques are clearly paramount. The selection of the processor, the power management IC, the battery, and the harvester are completely critical. You have to get it right or it will fail. And hydro, geothermal, wave, wind, and solar are variations on a theme which we're not talking about today because they're on a kilowatt and a megawatt scale. But obviously they tell us that it's perfectly possible. I mean, the Swiss railway runs on hydro. So even though Switzerland has 2 nuclear power stations, they specifically don't use the nuclear for the railways. The railways are self-sustaining, sustainable railways. And it's kind of a matter of national pride. They don't burn fuel for transportation, except in diesel buses, which they try to replace with things like gyro buses, and of course the electric buses which are now coming into service, will be very valuable. Now, the last point here, electromagnetic power transfer is exploding in performance, from milliwatts up to kilowatts. So we have chi, witricity, and power mat, and basically the standards for the transfer of energy between a charging pad and an object like a phone that wants to sit on the dashboard and get charged. Those standards are already set, but the witricity has now been incorporated in this. Worth reading about. Basically what the patents behind witricity say is that if you get the circuits to be in resonance, you can go 10 times the size of the coils. So you're extending the near field in a spooky way, and basically the first patent which is cited in the patents is that of Tesla. So there's an acknowledgement of the fact that the visionary Tesla had it at least partially right. He thought it would be possible to transmit power across a distance, and turns out he's right. He just didn't have hope with the technology. But now that we have the technology, we can make resonant circuits that self-tune. And suddenly we can start having the idea of of a room charger, which simply sits in a room and waits to see somebody coming in with a hungry device. And they'll identify each other by wireless, of course. And the guy walks in with a hungry phone. My phone is hungry. And the machine in the corner presumably will say, for $3.27, I will give you, I will charge your phone. Is this a deal or not? And so there's a way to monetize the transfer, because just where Tesla couldn't monetize, thus he lost his company. He had no mechanism for metering his power. Now we have, because they have an intelligent discussion between the demand for the electricity or the energy and the supplier. I'm sorry again?
Power efficiency for the actual magnetic.
The Witricity are showing a 50 to 60% power transfer at a distance of 6 to 7 meters. Okay, but you have to be resonant. You have to be really on top of the resonance. But it is extraordinary. So the original photograph shows the team with a about 24-inch coil on one side of them, and a 24-inch coil with a light bulb hanging on it, and it's a 50-watt light bulb, and they're putting 100 watts in on the other side of the table.
How big were those coils?
They're 24 inches, and that was resonant at just under 10 megahertz. And there's now a whole slew of patents, and Witricity is in fact signing up everybody. So it's not available to the general public, but you will find the discussions. If you Google Witricity, you'll find it all. So why AC power is not readily available? You can't afford to change the batteries. This is the whole current world in which there's coin cells everywhere. This drove us mad at IPS, where I was doing sales and marketing, because you've got a 10-year value proposition. How many times are you going to change the batteries, and who's going to do that, and what's it cost? And it turns out that batteries are ridiculously expensive compared to line power, and sending someone who has to be paid to do it, to change the batteries, is beyond belief, and it's an unknown rising cost. So you can't have a business model which is dependent upon an unknown rising cost. So it's all anything with a coin cell in it, frankly, is experimental. It probably won't stick as a commercial project. Exceptions today exist, like blood glucose meters. People put a coin cell in a blood glucose meter because it's a matter of life and death. If they don't take their glucose and don't get their insulin, they die. So they'll pay for the batteries, but that's okay. But notice it's the consumer himself who changes the batteries. Now it's feasible. But in a business where you have a maintenance man going around checking wall thermostats, it's not going to work. So traditional solutions, battery solutions, are too big or heavy. Think about UAVs, unmanned vehicles, drones, now growing very, very fast because lithium is the lightest metal, and therefore the batteries are now light enough that you can see the possibility of battery being put up in the air. But Europe is legislating to encourage alternatives that are less polluting than primary batteries. So this means that all those TV remote controls really shouldn't have AA cells in them. And it's already perfectly feasible not to have AA cells in your TV remote control. It's just a question of how long it's going to take. You want to increase the product lifetime and reliability because you want to eliminate the battery contact. The most dangerous place in a system with a battery in it is where the battery goes in. The box is no longer sealed. The contacts maybe go wobbly and loose. And where the application is deeply embedded or implanted, changing the battery is difficult. So implantation of pacemakers is relatively common these days. The biggest problem is pulling them out to change the battery. The explantation process often kills the patient because the device grows in and is now part of you, and getting it out is serious surgery. So having an implantable that is rechargeable through the skin, but it's a long-lived rechargeable battery. So this is not your conventional battery which typically has a lifetime that really can't go beyond 10 years. So sometimes it's just more convenient to cut the cord. So cutting the cord isn't easy, and here is the list of things that you have to think about with our little model. And the key one to keep in mind is you must have more going in than out, but it doesn't have to be at the same time. So as long as the accumulated area under the curve of energy in is greater than the accumulated load over time, then the thing will fly. And if you can easily have a situation where demand can be cut back. If there isn't enough energy, you can simply put out a signal that says battery low, you're getting partial data, I'm doing my best, when there's more energy available, I will improve the service. That's the sort of dialogue that will take place in this environment. So very important is energy storage, power management, and to be aware of all of these things. And wireless is a very good place to make improvements. So here is a slide from Laura that was actually shown yesterday, and I borrowed it. Let me try and interpret it for you. Data rate going upwards gives us various standards. So Wi-Fi is really a high data rate service, but it's horribly expensive in terms of energy. Battery-powered Wi-Fi isn't feasible. So, and cellular, we know that battery-powered cellular telephones are almost not feasible. I mean, we are driven mad by how long the battery lasts. You think a Tesla automobile gives you range anxiety about, can I get 250 miles? Ooh, I need to go 200 miles. Will I find a charging station? Well, everybody's got the problem with, is my phone going to die before I finish the day? This is very expensive in battery terms. And there's no way that that's going to be powered by batteries. But if we start throttling back the data rate, we get to these standards like BLE, which of course is subject to my later presentation. And then we have some other really interesting. Here's NFC, which is basically passive transfer of energy and data in a short distance for reading credit cards, for example. And then RFID, which has a range of possibilities up to 10 meters. Now with new technologies, new resonant technologies, some amazing results are being found with like 100-meter range at a gigahertz. Sorry? Yes. And then there's Z-Wave and another standard. So where are these things? What turns up in that spot? And it turns out to be all the things that we actually want to do. They tend to be low data rate. So it's really worth understanding that for low data rate transactions, you really don't have to use the high data rate devices like Wi-Fi and cellular. And therefore, there's a huge business opportunity, as was pointed out yesterday, for LoRa, a new low bandwidth standard with very low costs. Okay, so the choice of radio is critical. Here's our friend, the phone, because the customer is going to be able to inquire about what's happening, whether it's a mobile vehicle or a home automation system. I mean, maybe the customer's in his office and wants to know who's opening his front door. There's checking the state of oil tanks or flow lines, checking out of limits, is your pool flooding, the kind of information that very, very low data rate information can be collected over public or private networks and sent through to the cloud, stored for a fee, and then the customer pays to see the data. Now that business model is fundamentally the way that the aggregation of a great number of Internet of Things applications is going to be achieved. Looking at the LoRa data, you can now begin to see the powers involved, the fact that the radios can be made very, very sensitive, the data, by keeping the data down, by reducing the spreading factor if you can afford to do so, but if you have to, if the noise is really bad, you increase the spreading factor. But for me, what we're deriving from this is the question of, here's our AA cell, 2800 milliampere hours in an AA cell. It'll power one of these things for this length of time. Do you feel that it's justified to, if the product only has a lifetime of a couple of years, great, ship it. But if you have a value proposition like something down a manhole that's measuring flow for a utility, and what were you avoiding? A man going around reading meters. What are you substituting? A man going around changing batteries. Duh, that's not going to work. You've got to have a sustainable replacement for that battery. But by keeping that data rate low, you have a very real business case. So the first place where harvesting has been turning up is substituting, when available, for a primary cell. So you have situations where the primary cell will be included in the application, and if the lifetime is short, you can imagine shipping it with no harvesting. But as soon as you've got a value that says I've got to have this many more days of operation to make my case, then at this point you start thinking about adding this extra layer of substitution with harvesting. And that's essentially been the model that's being commercially applied in most cases. Such supplementary harvesting is seen now in a smartphone, a Kyocera smartphone, with an energy collector, photovoltaic energy collector, built in as part of the device. And Ohio State University's found a way to make smartphone batteries that last up to 30% longer on a single charge by capturing wasted RF energy and feeding it back to the battery. I guess that proves that the original cellular protocols were pretty inefficient. The fact that you get to the tower and have this amount of wasted. But you've heard the phone when it's trying to get to the tower, making these incredible, and taking an ampere of current to kick through the ether. It's very, very battery intensive. And so he's a bit cheeky. They're actually simply sniffing their own signal on the way out and feeding it back into the battery. 30% improvement in battery life. That's not to be sniffed at. Suddenly your 6-hour battery is now an 8-hour battery. So maybe it's worth doing. So here is the range of powers of typical devices. Power tools over at the top right-hand corner, laptops, GSM cell phones. I would have said typically harvesting is just marginal, and that's why I've shown a cell phone and a discussion on a cell phone. GPS is definitely workable with energy harvesting. One of the demonstrations we had at my company was a dashboard-mounted GPS, which simply sat on the dashboard, and when you got back to the office, you plugged it in to the computer, and it would show the map. So it had actually collected the GPS data in a memory, powered entirely by the sunshine on the dashboard, and showed your journey. So that kind of, although GPS is expensive in energy terms, it's doable. Don't try and run a display. If you want a display, then you'll use the GPS in your car, and you're using the car battery and the engine. So Bluetooth, old Bluetooth that is in fact, shown there, and then hearing aids, sensors and remotes. Now we're getting into the sweet spot for where we are really concentrating. Then the RFID tags, which are, in this case, active tags. Then there's watches and calculators and real-time clocks. And we're down now to the very low powers, which are feasible and reasonable to be powered entirely by harvested energy. So how much energy is available? The top device is a room-powered mouse. So here's your mouse. Instead of an AA cell or a AAA cell inside it, it now got a jazzy-looking piece of photovoltaic. and talking about energy, power, microwatts per square centimeter up to milliwatts per square centimeter. Then the second device is a quasi-resonant vibration device with a proof mass which bounces up and down. These devices typically are tuned at a particular frequency, and there are now MEMS versions of this, which are relatively broadband and able to harvest a certain amount of energy from any object that's buzzing or vibrating and giving you power without having to be wired. Then there's the current thermoelectric. That's a breadboard. The thermoelectric device itself is squished in here. It's in there, and you're just working between the cold side and the hot side. So you put this thing down on a hot plate or a hot object. And today in Europe we have central heating, radionic systems in which the device starts reporting the temperature. When there's a 2-degree temperature difference, it'll start reporting. It'll suddenly just wake up with 2-degree temperature difference. That's basically the system kicks itself into life, and from that tiny different temperature makes enough power to start transmitting information, and a little bit warmer, and it's able to power the valves. So the system is entirely self-powered. You put fuel in to run the central heating system, but the entire regulation of the system in all the rooms and so forth is the zones is done by energy that's not wired. Then there's a resonance stick there, which is in the 915 meg band from Powercast. And then at the bottom, I've shown the NFC. This is work that was originally done by Philips NXP, and this is the heart of your credit card or your NFC transfer in your iPhone, or so device-to-device communications at a distance of 1 centimeter. And there's the powers that you can transmit. So the NFC 13.56, actually lots of energy available. We were pulling 6 to 7 milliamperes off a card reader. So charging a battery quite fast. So storage, primary cells, they have high discharge current, though not that high, high energy density, and they're inexpensive, but they are limited life. The replacement labor cost will kill the business case if you actually pay someone to do it. They're ugly. People feel bad about them. The nickel metal hydride is very popular and familiar and chunky. It has maybe 1 to 200 recharge cycles, decent energy density, but is more expensive, and it has to be recycled. Certainly in Europe, everything has to be separated in a separate waste stream. And then rechargeable lithium ion is well known. The fact of the matter is, if a conventional battery works, use it. It'll be cheaper and easier to design in, but if you have a case where you need to be off-grid, you're going to have to go beyond these guys. Now, thin-film batteries were developed in the USA at Oak Ridge National Laboratory in the late 90s. And they use all solid-state chemistry. And the Oak Ridge technology was licensed to Symbet, Planar Energy Acceleratron, FET, Infinite Power Solutions, and ST Micro. FET and ST Micro are the only commercially available thin-film batteries today. And here we're talking about postage stamp size devices. They look like this. And there's the scale of this thing. So this is a 4-volt battery with a about the size of a postage stamp, and perfectly capable of pulling 20 milliamperes to 30 milliamperes, and able to run radios with ranges of up to 1,000 meters from a battery that you really can't see. And this is the commercially available product from ST today. These are familiar supercaps, which are developing fast, and they're not as energy dense as batteries, but they have fabulous fast discharge capabilities. So for pulse work, they're brilliant. But they had been in the past leaky, and they have certain disadvantages, but they're getting better all the time, so very much worth thinking about. that's an FET device. These come out of California, and they're being shipped commercially now, and there's factories being built. ST's building a factory right now, commissioning it with a couple of million pieces per year capability. Frontage Technology have a factory going in China, which will be on the air within the year.
What's the charge cycles for the thin film batteries?
Well, that's the amazing thing. This one, done right, you're talking about 10,000 cycles. It's completely different from the lithium-ion. Lithium-ion, 500 cycles, 1,000 if you're really, really lucky. A rapid fall-off, quite high leakage. These things leak in the nanoamps. So they basically have a 10-year storage life. Just charge them once, and the 10 years later, they're still good. And if you've been charging and recharging them, they're also good in 10 years. So they're really special.
Passivization issues?
Absolutely. Absolutely. You have the art is in keeping the water in the air out of the lithium. That's not our topic for today. Happily take that offline. It's important is to just I think I've got it here. Yes. Now, before I mention them, there's a company called Ilika in the UK, which is now going into the thin film battery business. So, perhaps I should explain what happened to IPS. What's Richard doing here? Well, the company died, and the intellectual property was bought by Apple for cents on the dollar. I think they think it's very useful. I can't imagine what they'll use it for, can you? Imprint Energy is in California, and they are making a zinc-based rechargeable with several hundred life cycle, with a 1.5 volt technology. So it's a zinc manganese system, printed, so atmospheric printed, with technology from Berkeley. And they have told me that they now have an industrial partner who is not to be named yet, but by next year they'll be named, and they will be going into high volume business. So this area is not by any means dead. It is growing fast, and the beauty is the pull from the industry, from gentlemen and ladies like you, is super important. So to summarize, bulky batteries are useful. Coin cells are fine for backup. Supercaps are best for the high current loads. Thin film batteries are best for the low to moderate power energy harvesting apps, very thin applications such as powered credit cards and apps requiring a high number of charge cycles. Be cautious at low temperatures. So now let's look in practical terms. Here's the smartphone as a portal. And one of the things that we have in common between, just pull that back. One of the things in common here is that once you've chosen the smartphone and you have a platform, you are going to use BLE, because that's just become the platform standard. So what is a BLE beacon? And the answer is there's a whole range of devices now coming out. And first of all, the simplest beacon is called an advertise only, and it basically just says, I'm me and I'm here. And it transmits this information to everybody, and you just have to be looking for that signal. And what's it for? Well, it's people are using it in supermarkets, for example, so that if you have if you're a loyal customer of the supermarket and you typically buy beans, as you go by the beans will have a beacon on, and your phone will go bleep, don't forget to buy your beans. And very mundane, but this sort of geofencing application does have serious uses as well. The key thing is the potential market is huge. It's typically disposable. Most all of the commercially available devices today use a coin cell. And apps exist, and of course you've started now downloading an app. You've got one in your phone. So geofencing, context awareness, but beacons can also broadcast real-time data wirelessly. So the first beacon that got people's imagination, of course, was the Apple iBeacon, which is an Apple proprietary standard, and it has its own standard for the beacon interval and for the packet format. Essentially, it's an active RFID based on a BLE, on BLE standard or BLE Smart, Bluetooth Smart. But it's caught people's imagination. It's very easy to start improving on this, but advertising only, just simply saying here I am and here and this is me, so it's a unique code that's transmitted, has all sorts of payback possibilities. Now, here's what the thing looks like if you put it onto the analyzer. Now, this is the EM beacon, which I'm actually going to be showing you. And the EM beacon specifically runs 2 cycles of advertising. It advertises as an iBeacon, but it also advertises as an EM beacon. And the difference between the protocols is very small. It's just to do with the length of the data packet. But what's important is that you can predict, because of the way that the thing works, you can predict how long the battery will last. You can easily imagine these beacons, lots and lots of them, making it into the cloud, because the smartphone that's nearby picks up the data and does the cloud transmission. And that aggregation of data is of value. So the beacon hardware is simple and inexpensive, just transmits. It's an ID, but it could be a measurement, it could be a fact. Smartphones are ubiquitous, powerful. The fact that I've managed to get most of you to pull out of an iPhone, a smartphone and do something with it tells you just exactly how many. How many people have actually connected? Okay, so good. 1 billion points of presence. They can do complicated things, and we'll look at that. We can customize the beacons with extra sensors, so analog, photodiodes, accelerometers, for temperature, pressure, humidity, proximity, and the firmware can be updated. You define your own product to provide differentiation in the market. That's one of your Renesas buzzwords. So EM Beacon for Renesas was developed last year and is available for the RL78. There's a demo kit, software code and library requiring no stack, compiles under E2 Studio and can be customized. So if you're interested, you can already get to work with this, and there's obviously a lot more going to be done. So just to bring together now these devices, this is the device that's running on the Apple iPhone using the tiny URL. Now, has anybody got that running? Have I got it? Do you have an iPhone? Could you pop up, Alejandro? Okay, well, bring it up because we can put it on the screen. Oh, you've only just powered it. Okay, so the little guys that are supposed to start turning up here, look like that. That's not very much of a picture, is it? Perhaps I'll pass one around. It's a beacon with a little solar cell on it. No stealing, please. And here's a... Here we go. We've got a vendor 2 sensor 1. Let me see if I can activate that. Aha, okay, we're up. Once these things get energy and light and the app's running, they start, the key thing is no battery. You simply put this thing on a wall and you can now start reporting your room conditions via Bluetooth, as in, that was easy. That's all there is to it. And these apps are available to you. This work was done 2 years ago at Zurich School of Engineering at Winterthur. And okay, I think I have one here as well. I think this is probably the one. Ooh, didn't like that, did it? Oh. Phenomenally on. It's getting pretty humid in here, isn't it? Yeah. Yeah. This is a Swiss humidity sensor and a very obvious temperature sensor. But okay, that's that one. So let's go back to the presentation. Got 5 minutes to go. Okay. Now, the EM beacon differs from the iBeacon because it has the extra bits added to it. So this is the data packet with addresses, beacon-specific addresses. So as soon as you get into the Bluetooth Smart SIG and start reading the literature, you'll find all the standards there, and getting into this is really simple. And there's lots of vendors now who are happy to help you into this business. And let's see if we can make some use now of this extra information that's available on this beacon. So let's have a look. So if we switch to the EM beacon, so those of you who've got the EM beacon running, okay. Right. Here we go. Now if I tap on that, okay. So this is this guy. He's now this is EM's batteryless. This is a batteryless version. So this is EM, who make coin cells for the watch industry. They are the Swiss watch industry. Have decided that it's high time to start using solar technology. So they've started this work finally. And let's see if I can. Cool. Eh? Right. Let's see if I can let's see if I can add another beacon to the group. Oh, here we go. And here's some more beacons. Now this guy, I'm going to go into that mode. And let's have a look at this one. The first beacon. See how? Oh yes, you see the packets now. So we can. This guy has got his accelerometer activated now, and we can see the data. I'm sorry, the efficiency of the antenna and so forth, because this is obviously a tiny printed antenna in here, and this you see the package transmission occurring. And if I go to device number 2. Here, I'm not yet seeing it. Basically, one of these is set up to detect falls, and the other one is to detect movement. And this is just there's a little state engine in there, and you flip the states, and you're able to use this thing. So you could put this beacon on your laptop, and your laptop moves, and you'll get a Bluetooth message. So somebody moved your laptop. Is that what you intended? And so on. Okay. So there's the Finder app. There's the report that you've just been looking at. And those are the modes that you step through with the little beacon, and it goes from sleep mode to sensor mode to moving mode to full mode. And that's dead easy coded firmware that's made available freely with this product. And but mainly it's to show you what's possible. So in summary, I propose that the smartphone and the cloud change the game. We outlined a typical low power sensor, we reviewed the principles, and we saw a working beacon example. Any further questions? Can I have my parts back? I'm missing one blue thing and one white one. Where'd the blue thing go? Who's got the blue thing? Don't let the people out with the blue thing. Still in use. Okay, cool. Thank you. Okay.
One question with is that powered strictly by the battery during transmission, or do you have a particular type of capacitor in parallel with that you're using to boost the current?
Which device? Because the answer is the ones with the solar panels have got no battery. There is a I think a super cap. Yeah, there's a capacitor, sure. Because you never know. I didn't go into detail this time, but of course, the clouds go over the sun. So as long as you've got something that gives you some lifetime, like maybe it's only 20 seconds.
What the optimal capacitor type would be for that application, I guess is more.
Everything would be specific to the purpose. I wouldn't speculate. You've got to trade off size against leakage. Normally, I think in terms of needing energy storage seriously, because so many applications use day and night, and you've got to survive through the night. Therefore, your storage system's got to be seriously capable of doing half a day's work without any energy input. Okay. Any other? Yes, sir.
The wireless power transmission.
Wireless pattern.
Yeah, you say 50% efficiency, so the other 50% burn into the transmitter coil.
Yes, it's just basically you are the physics of the resonance is the famous story about the baby sinking the battleship. If you stand, you've not heard that story. If you take a ship and it's at the side of the quay and it has a rope on it, and you stand on the rope, the ship will move a little bit. If you know what the resonant frequency of the rocking of the ship is, and you keep on adding an impulse to that each time it comes to the top dead center, as it were, you will start increasing the amplitude of the oscillation. So a small leverage of the input will cause a resonance to occur, and it will rise and it'll increase, and the amplitude will go up. This, in other words, as long as there are low losses in the resonant circuit, then you can you're then basically restoring what you're taking out once you've got it resonant. That's the physics of it. The answer is 50% at that distance. Clearly, if you increase the distance, what I suggest is go to witricity.com and see it. They'll show you resonant repeaters, where basically you can now have a lighting fixture separated from the power generator by a distance of 20 feet or more, by having a repeater. So the first repeater resonates with the transmitter, and that resonating repeater then sends power to the lamp. It's not obvious, and then you say, whoa. And it clearly is so important that it's completely changing the way that cars will be charged and lights will be lit.
Does that follow the inverse square?
No. 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 It's cool. It's got patents, yeah. Right. Okay. Okay, thanks, guys. Thanks.